presentation notes and then get ready for our quiz. Probably have some time to work on that, the last sheet of the worksheets that I handed out. So we start off with a look at the difference between displacement and distance. Okay? No, they're not the same thing.
I think all circumferences are zero because the displacement and distance is the same and the displacement is zero.
So if you take a ball, if we take a ball and we throw it up in the air and catch it in the same place that we threw it up from, then the displacement is 0, but the distance, it's gone up 2 meters, come down 2 meters, is 4. No, I don't think I did either. I'd hit the roof. Okay, I think this is why I don't like running, because you go out your front door, you run around the block, and you end in the same spot. And I say to myself, I could have got here a lot quicker had I not left. Right? And so, but, so since displacement is the integral of velocity, well, we should almost have an S here, right? There it is. Then the distance, whenever it's going in one direction, it'll be positive. Whenever it's going the other direction, it'll be negative. You have to figure out which parts are negative. And if you think about the area under the curve, you're going to have to find out where your x-intercept is, and then any negative displacement will be considered a positive distance. All right, so here we've got velocity, and we've got an equation with the sign. Find the object's displacement over the first 3 pi over 4 seconds. So we're wanting to find the integral from 0 to 3 pi over 4. So I'd like you to write out the integral yourselves. And there should be, we can't see it, there'd be a little dt there, right? All right, check, how did you do? Now, it wouldn't be bad if you had put the 2 there and had divided by 2. I don't mind that, because you're going to have to undo the chain rule with the integral of sine. And it needs to be in negative cos, because the derivative of negative cos is negative sine. And now we get to practice our pi plate. Cos of 3 pi over 2 is equal to 0. Now this is the displacement. It's traveled 1.36 meters away from its original spot. But what is its actual distance over the first 3 pi over 4 seconds? And if we look at this graphically, and I graphed it on the graphing calculator, part of the velocity graph is above and part of the velocity graph is below. So what we would first have to find are what are these points? How do we find that? We'd have to set our velocity equal to 0 to find out what parts of the curve are above, what parts of the curve are below. Setting it equal to 0, and solving for sine 2t, you get sine 2t is 1/2. That's a value. A half is a value on your pi plate. That's your pi over 6 family. So the inside would either have to be pi over 6 or the inside would have to be 5 pi over 6. Does it make sense that you would get more of them if you kept going? But when we divide these by 2, these are the only ones that are before 3 pi over 4. Like, had you found the next one would be at 13 pi over 6. But when we divide that one by 2, 13 pi over 12 is past 3 pi over 4. So sometimes you might actually do that extra point just to make sure, oh, I don't have to do any more. So the blue area will be positive, the purple area will be positive, and the red area will be negative. So when we set up our integral, we'll have our integral from 0 to pi over 12. Our integral from pi over 12 to 5 pi over 12. And our integral from 5 pi over 12 to 3 pi over 4. I'll just give you the answers. I'm sure you could do them. These are plus signs, and these are t's. Yeah, it's 3 pi over 4 on the top. Question. Can you see how if you only calculated this and what you did in part A, you could figure out the answer? You'd have to add it twice. Why would you have to add it twice? Yeah, if we think about the original answer would have been these areas and then this area subtracted. So if you added the red area once, you would undo the subtraction. If you added it twice, now that's only if you had already done that in part A that would be helpful. If they just asked you the distance, then you'd probably have to calculate all three of these. And then one other one, and then you only have to calculate two. Not a bad idea. Mm-hmm. All right. golf ball. You decide to climb up a cliff 75 meters high with a golf ball. Nope. This class is dangerous. So there's our cliff, 75 meters high. There's the happy you with the golf ball. Throw the golf ball with a velocity upward of 7 meters. Now, it doesn't mean you have to throw it straight up, right? As long as the velocity upwards is 7 meters, it could be thrown forward at the same time. No. You could use formulas, but then you would need formulas.
Yeah, I have the formulas.
Well, okay.
We did this in physics class.
The nice thing about the calculus is you don't need the formulas. So what do we know about this situation? We know that when time is equal to 0, our initial velocity is 7 meters per second. And we know that when time is equal to 0, our initial displacement is we're 75 meters above the ground. What we want to find is how long it'll take the golf ball to hit the ground. Well, we'll see. We'll see if it's easier without calculus or not. What do we know? We know that there's gravity. And you know that the gravity is negative 9.8. If we integrate the gravity, we will get the velocity is the integral of the gravity. And what variable do you want to use? T? T for time. And so we get our velocity is negative 9.8 t plus c. And since we know our initial velocity is 7 when time is 0, we get that our c value is 7. So now we have an equation for velocity, that the velocity is negative 9.8 t plus 7. Integrating this again, we'll get our displacement. That's exactly like kinematics form. You always have this over 2. And this is your initial velocity is always there. Well, you know that why? Because of calculus. You don't need to know why. And now we can figure out that our initial so your d value is 75. And we now have a displacement formula. There you go. Negative 4.9 t squared plus 7t plus 75. What do we want to find out? We want to find out when the ball hits the ground. So then our displacement, comparatively to everything that we've done, if we started with our displacement 75, saying 75 meters above ground, when it hits the ground, we're wanting to make the displacement 0. Now, in real life problems, it usually works out that they don't work out to be factorable. as in this case, that is not a very nice thing to factor, so we're going to have to use our quadratic formula. T is equal to negative b plus or minus b squared minus 4 times a times c times 2a. So we're going to have to go to our calculator here to calculate these. You can do that in your head. That's wonderful. He's just going to verify once I put the answers up. Here's one answer. Okay, we need to have units here now. This is a real-life problem that we just solved, and so we have a problem with this answer, being that it would go back in time. When did it hit the ground? 3 seconds before I threw it. Or this is how much time it took you to climb that 75-meter cliff. That's pretty. You'd just be accelerating at 9.8 meters per second as you went up that cliff. So our only answer that makes sense is 4.69 seconds. And now your kinematics formulas are explained. You just like people telling you formulas that work and then you don't have to know why? Yeah. So you have the people that give you formulas, then you could also hire people that look at the answer in the back of the book to all the questions and tell you it. That would be good too. And our last example. Nathan designed a car that has a constant acceleration. I don't know, maybe that's good for fuel. That'd be a good question, right? Yeah, there you go. Here's your new IA. You figure out whether or not, what is the best acceleration for fuel to reach your, that is a good question. And then if you had that, you could name your car like Alexa, and you say, get into your vehicle, and you'd say, Alexa, reach 100 kilometers per hour. And it would automatically accelerate to that speed at the best fuel consumption as possible. Okay? But in this case, Nathan designed it so it has a constant acceleration. So one day he set out on the highway, he just sort of turned onto the highway and hit the button, and off he went. And he got to 100 kilometers per hour in 20 seconds. How far did he go in those 20 seconds? There you go. You use your physics formula, and we'll do it in calculus form. Oh! So what do we have here? We have at time 0, velocity is 0, and displacement is 0. We're given that. We're also given that 20 seconds later, our velocity is 100 kilometers per hour. Now, the problem is that we've got this question asking for an answer in meters, and our time is given in seconds. How good are you at changing 100 kilometers an hour to meters per second? There we go. Some people know you need to divide by 3.6. Others would have to change this from kilometers to say that that is times 1,000, 100,000 meters. And the hours show that that is 3,600 seconds. Simplify that. It's the same as dividing by 3.6. If we go to our calculator, 100 divided by 3.6 is 2.7 repeated, which as a fraction is 250 over 9 meters per second. Now, initially, we might feel in this question that we're a little bit stuck because we don't know what the acceleration is, but we could just assign it some constant. We know it's some number. We'll call it k. If the acceleration is k, then our velocity would have to be the integral of our acceleration, which I'll put in the value of k. I'm not using any formulas. Okay, well, we'll look at it this way first, and we'll see where we go from here. You're using a formula there, though.
Is that not a formula?
This is just an integral. This is just using. So what do we know? We know the velocity at time 0, or at time 20, sorry. First of all, okay, we know the velocity at time 0 is 0. So we can solve that c has to be 0. From that, we also know that at time 20, the velocity is 250 over 9. Simplifying this, gives us that k has to be 25 over 18. Just using calculus. So you took your, you just did the formula, speed over time. Yeah. Now that we have k, though, we can figure out that the displacement is the integral of our velocity, which we now know is add 1 to our exponent and divide, plus d. And again, since we know time is 0 and displacement is 0, we know that our d value is equal to 0. So if we want to calculate the displacement at 20 seconds, we would just have to calculate this. As a fraction. So you go about 300 meters to reach 100 kilometers per hour in 20 seconds. Mm-hmm. No, because if you have that knowledge already, unless the question said using calculus, then
Can I just use calculus for like the first part of the question? I would have used calculus.
but it's kind of nice to see where the physics and the calculus come together, how they're related.